Good morning, class. Welcome back to our ESci132 mechanics of deformable bodies. And as you can remember, last week we have started our second module, which was about the mechanical properties of materials. And we have talked about the normal stress strain diagram. We have also talked about the tension test. And we also talked about brittle and ductile materials. And now, we will continue our lesson on this second module, and we will now talk about the Poisson's ratio. So the main goal of this lesson is that we will learn the concept of Poisson's ratio and how is the longitudinal strain related to your lateral strain. And unsa naman po na nga mga terms. We will learn that one as we continue on this lesson. When a deformable body is subjected, let's say, a tension, diba, we all know that that body will elongate. If we say that that body is deformable, it will elongate, and also, at the same time, that the lateral cross-sectional area of that body will contract. Sige, let's say for example, I have a shaft. Okay? I have this, let's say, a deformable shaft, a homogeneous shaft, and this shaft is subjected to tension. Okay? Now, again, we have learned that when this shaft is subjected to tension, it has the tendency to elongate. So therefore, this length is going to change. Right? But at the same time, as the length of the material elongates, the lateral length of this material will also at the same time contract. Okay? So let's say this is your diameter. So, let's say kung na-deform ni siya nga object, then it will actually look like this. Naing-ani ang atong object when it was deformed at the tension that we have applied to it. So therefore, ni-elongate ang atong shaft and also mi-contract ang iyang diameter. This axis is what you call the longitudinal axis. Okay? Longitudinal. And this axis from here to here, this is your lateral. Okay? So therefore, you have a relationship of your longitudinal axis of your shaft and its lateral axis. Okay? And they are related to an equation. And that equation is what you call the Poisson's ratio. And take note, this is very important. Your Poisson's ratio can only be applied when your material is behaving linear elastically. What does that mean? Your Poisson's ratio can only be applied when your material is elastic. Kanus ara ganito elastic ang atong material? When it is still under this curve. Diba na atay ang ani nga curve? Ing ana? And diba ato to gi-identify nga ang kani nga region diri is your elastic region. So, your Poisson's ratio can only be applied when your material is still on its elastic behavior. So, once na gani niabot na ang imong stress, nilapas na ang imong stress sa imong material beyond the elastic behavior of the material, then you cannot apply the Poisson's ratio. Just the same as your modulus of elasticity. You cannot apply your modulus of elasticity whenever your material is now on its plastic behavior. Because why? Again, the modulus of elasticity is basically the slope of this one. And you can apply this slope in this curve right here when it is now behaving plastically. Okay? So therefore, that is when you can apply this Poisson's ratio. So what is then ang atong Poisson's ratio? How is your longitudinal strain and lateral strain related with each other using our Poisson's ratio? So basically, your Poisson's ratio has a unit of nu. Okay? Nu or V nga murag R. Okay? And you have a formula of your Poisson's ratio as the negative strain of your lateral divided by your strain longitudinal. So this is the equation that you have to use when you are using your Poisson's ratio. And your Poisson's ratio actually will just range from 0 to 0.5. So once your Poisson's ratio goes beyond 0.5 or goes lesser than 0, then that is impossible. Why? Because I don't know. Why isuot sa book? Okay? Typically, for non-porous solids, the value ranges from 0.25 to 0.355. Okay? Question. Sir, nganong negative ang atong equation? Why is the equation negative? Why? Sige, ato tan-awon ang kaning kuan. Di ba we already knew that you have the equation of your normal strain, which is equal to the final length minus the initial length over the initial length. Di ba? You can remember that on our previous topic, on our previous topic. And sige, let us assume nga kaning beam that is, or let's say shaft that is subjected to tension ang atong i-consider. So with this equation, unsa man ang result ani nga equation, will it be positive or negative? If your LF is longer than your Li, then you can say that this equation is positive. Right? When we are talking about the longitudinal strain. How about if we are going to talk about the lateral strain? What will happen? The same formula we're going to use, but instead of using L, let us say, ato gamiton og diameter. DF minus DI over DI. What will happen to our equation? What will happen to the sign of this one? Since we know that if ang imong shaft mo elongate siya longitudinally, pero on the other hand, mo gamay po ang iyang diameter. So therefore, your DF is lesser than your DI, and obviously, your answer here will be negative. So, ato na i-apply ang equation. Strain lateral is negative over strain longitudinal, which is positive. What will happen? Your Poisson's ratio will be positive. Kaya dapat ang atong Poisson's ratio is always positive. Because it is impossible for an object nga gi-subject into tension nga mo elongate siya and at the same time mo baga siya. That is impossible. Because it will always go on the other hand, in the other way. It will elongate and at the same time it will contract. And if you will contract it longitudinally, mudako po ang atong diameter laterally. Okay? So that is why you have to use the negative sign so that your Poisson's ratio will always have a positive value. Okay? Understood? Let's have here an example. Let's say we have a bar that is made of a type of steel A36 steel, and its dimensions is shown in the figure. So it has a length of 1.5 meters, it has a width of 100 millimeters, and it has a thickness of 50 millimeters. And you have applied an axial force to this beam, to this bar, a tensile axial force of 80 kilonewtons. Okay? And we have to determine the change in the length of the bar and the change of its width and thickness of the bar. So how are we going to solve this problem? And take note, it is said here that this material is behaving elastically. And again, if the material behaves elastically, then when you have the type of steel that you are talking about, makitaan lang na nimo sa internet ang iyang modulus of elasticity because that is constant always to that kind of steel. Okay? And let's say, given na ang atong modulus of elasticity with a value of 200 gigapascals. And also, with the same type of steel, you also have a constant value of your Poisson's ratio. And it is said here that your Poisson's ratio of your steel is 0.32. Okay? Again, you can just search it on the internet or have it on your books, on your references. Okay? Sige daw. So let's try to solve this problem. So what we are required is to know the final length, to know the final width, and to know the final thickness. So how are we going to solve that one? It's kind of tricky, right? Okay, ang atong example kaganiha was a shaft that has a circular cross-section. So how about when we are talking about a rectangular cross-section? It might be tricky, but let's try to figure it out. So unsa may una nato dapat buhaton? In order for you to determine the change in length, the change in width, and the change in thickness, asa man nato makit-ani nga mga values, nga mga variables. We have it on the equation E for our LF, longitudinal strain, is equal to LF minus LI over LI. Makit-ani natong LF ani nga equation. And our gihatag ang atong LI, right? So we can solve for this is given, and is your longitudinal strain given? I don't think so. We have to still determine this one. So how can you determine that one? But before that, ato na po ni anhion nga kani nga equation. So your final width and final thickness can also be determined using this equation. The lateral strain, which is equal to either WF or TF. So WF lang ako ibutang dere. Again, this can be either WF or WI or your TF minus WI over WI. And again, your WIs are given at the same time. How can you get your lateral strain? Your lateral and your longitudinal strain can be determined where? By this equation sa atong Poisson's ratio, which is the negative strain lateral over your strain longitudinal. This is given, this is not given, and this is not given. So, once gani nga natoy usa nga makuhaan ni, then we can now solve the problem. Ma-determine na nato, makasolve na to sa LF, ma-determine na to, then ma-determine po nato ang WF o TF. So, how are we going to determine these values? We knew that this material behaves elastically. So what does that mean? you can apply the Hooke's law. Unsa man ang Hooke's law, wala na ko na-discuss before, but basically your Hooke's law is just your modulus of elasticity. So you can apply that law when that material behaves elastically. To apply that law, you have to use the modulus of elasticity. And unsa ganitong atong formula sa modulus of elasticity? Modulus of elasticity is just basically the rise over run of the proportional line, which is the stress over the strain. Okay? And you have the value of your modulus of elasticity given, and you have the value of your stress, not really, but you can solve for the value of the stress. And the strain that you can solve in here is actually your longitudinal strain. Okay? So, given in E, we have to determine your normal stress. So, how can we determine our normal stress? We all know that your normal stress is equal. Daghang kayong mga equation gipang balik, no? Oh my gosh. This is the normal force over the cross-sectional area. And maoning pinaka directly nato nga ma-solve nga equation. Why? Because we have a normal force that is given there, your 80 kilonewtons over your cross-sectional area of 50 millimeters times 100 millimeters. So your answer here is kilonewton per millimeter, and that is actually gigapascals. Okay? Your answer here is 16 megapascals. Okay? So 16 megapascals. Ganun ganing na yung ana? Di ba kay ang atong kilonewton per millimeter squared, take note, kilonewton per millimeter squared is gigapascal. Newton per millimeter squared is megapascal. Newton per meter squared is, kilonewton per meter squared is kilopascal. And Newton per meter squared is Pascal. Always take note of that so that dili na mo maglibog when you are solving this kind of problems. Okay? So now, again, you have your normal stress of 16 megapascals. And we can now apply this one in this equation. Right? Because we can substitute 16 in this stress, and you have given ang imong modulus of elasticity. And pila gani ito ang imong modulus of elasticity? So, sige. So, ito ibali. So, longitudinal strain is equal to the stress over the modulus of elasticity. And your stress, again, has a unit of 16 megapascals. So, therefore, it should be dimensionally homogeneous. So, dapat ang ato pod modulus of elasticity also has a unit of megapascals. So, it is given here that your modulus of elasticity is 200 gigapascals. So, therefore, this is 200,000 megapascals. Okay? So, divide. And you have here 0.00008, oh my gosh, millimeters per millimeter. Or, basically, this is 80 times 10 to the power of negative 6 mm per mm. Oh, so nanatay longitudinal strain. We can use this one to solve your LF. Sige, ano solve ang LF? Solve LF. Sige. Ito lang gamitan ng equation. 80 times 10 to the power of negative 6 is equal to LF minus what is your initial length? Your initial length is 1,500 millimeters divided by 1,500 millimeters. So, you can now solve for your LF, which is basically 1,500.12. Imagine, ing ana lang ka gamay ang changes sa atong length. This is so small, but you still have to consider this one on your solution. Okay, so na ako'y sayop gamay. na ako'y sayop gamay because the question is determine the change. Dili ang final length di ay. So ang change di ay of the length ang imong pangitaon. So unsa man, di ba? This one is just basically your change in length. Okay? And na-solve na natong LF. So 1,500.12 minus 1,500. So ang imong change in length longitudinally is equal to 0.12 millimeters. Okay? So this is your answer. Ang change di atong gipangita. Pasensya na. Understood? Now, we are not done yet because we also have to determine. Wala sayop dahil ni ako gipang butang dari. Dili ni ang final length but the change in the length, the change in the width, and the change in the thickness dai. I'm so sorry, but you can still consider that one. Okay, so how about we are going to solve for your change in, sige, ato na lang ni i-change diri. Change in width and change in thickness. So far, have you understood the lesson? I can't hear you, but I hope you did. Okay, so let's continue. We are now worried on how we can solve for the lateral strain. And as you can remember, we have an equation that is related sa imong longitudinal strain and lateral strain. And that is, again, your Poisson's ratio, which is equal to the lateral strain over the longitudinal strain. This is given, and this is given. So you can just simply solve for lateral strain. Okay? So therefore, your lateral strain is equal to negative longitudinal strain times nu. We have this equation, and with this equation, we can determine our lateral strain. Sige, so negative longitudinal strain, which is 80 times 10 to the power of negative 6 times your Poisson's ratio, which is given as 0.32. So the answer here is negative 25.6 times 10 to the power of negative 6. So this is your lateral strain. Okay? So this can be applied either on your width and thickness. So now we can solve for the change of your width and the change of your thickness by using this lateral strain. Because again, this can be applied on both width and thickness. Okay? Because both of them are laterals. Okay. Let's finish this one. So, ato to ibalik ang equation sa atong lateral. And instead of using this one, ato ibutang kay delta width. Mo na to ibutang. Kani siya, mo ning change in width. Okay? Sige. So, change in width is equal to the lateral strain times the initial width. Okay? So, pila ito lateral strain? Negative 25.6 times 10 to the negative 6 times your initial width, which is 100 millimeters. So, your answer here is negative 2.56 times 10 to the negative 3 millimeters. Okay? So this is your answer for the change in the width of your material. We're not done yet because we also have to solve for the change in the thickness. And we can just apply the same equation. Change in thickness is equal to the lateral strain times the initial thickness. Okay? So, balik ta. Negative 25.6 times 10 to the negative 6 multiplied by 50, I guess, mm. Wala na ako gikuan kaya nilapas na. And the answer of this one is negative 1.28 times 10 to the power of negative 3 millimeters. That is your change in. Ano, nag-red, blue, black ang atong colors atong box. Okay? So, since the change man ang atong question, ang atong problem, ang gipangayo, then the change ang atong ihatag. Okay? Again, why is this negative? Because the bar is elongating. The object is elongating, so therefore, the lateral widths of this bar should be decreasing. But again, if the longitudinal length of your material is contracting, then I'm sure that this one is negative and these two are positive. Okay, understood? So that's how easy our problem is, and that is your Poisson's ratio. Again, your Poisson's ratio is the the negative ratio between your lateral strain over your longitudinal strain. And I hope that you have learned its concept and you knew your lateral strain and longitudinal strain, because those two are very important when you're solving Poisson's ratio. And that's it for this lesson. So I hope you understood all of these things that I've talked about, and see you on our next lesson.